Hello, my name is Stephen Earls and I work as an area coordinator for the Further Maths Support Programme in Wales. I'm based in Aberystwyth. If there is anything that you would like to know in further detail or anything regarding these slides that you do not fully understand, then you can contact me at either of the two email addresses that are on the screen now. I regularly check both of them, so feel free to use either of those two addresses. Now, the aim of this session is to look at the applied maths, that is, the mechanics and the statistics as we develop from the knowledge that we gained in Year 12 and move into Year 13. Now, with these, we will look at developing the understanding of both of these. It's all well and good mechanically going through a question and just reproducing just for the sake of it, but we need to look at why things work and how to improve our understanding of how to solve these particular questions. Now, for both the mechanics and the statistics, I tend to apply what is known as the DAD system, and those are the first letters of draw a diagram. It is much easier when you're doing mechanics or statistics to have a diagram to give you some guidance. In mechanics, you need to know which direction is positive. So when you find your solution, if you end up with a negative number, it just means you were going in the opposite direction. When you've done hypothesis testing in statistics, if you've drawn a sketch of a normal distribution and marked the critical value, it's very easy then to see whether you're in the region that says you should reject or you're in the region that says you should not reject. So it's always very useful to have a look at the diagram. It doesn't have to be accurate, you don't have to use a ruler, but it just gives you some guidance. Now, in this session, I will start by looking at the mechanics side of moving from FM3 into FM6. Now, the first thing I want to look at in the mechanics section is momentum and impulse. Now, as it says there, we're used to doing this in 2D. Technically, we've done it in one dimension. We've just had 2 or 3 spheres moving along a tabletop and they crash into a wall. Now, the fact that you've got a wall, the wall is at 90 degrees to the table. That's why they tend to call it 3 dimensions. But effectively, they're moving in a straight line. One is chasing behind the other, or they're moving towards each other when they collide. Now, when you move into FM6, you're going to have things moving not in a straight line, but at angles to one another. Now, in that situation, what we'll do is we'll still think about it in terms of 2D and move into 3D. But if you can grasp the concepts using vectors in 2 dimensions, then there's no problem then moving onto vectors in 3 dimensions because you've set up the rules of how you're going to work. Now, in terms of that, if we look at an example. Now, this particular example, you've got 2 masses. The smaller mass, A, of 2 kilograms, and a larger mass, B, of 4 kilograms. As you can see, the velocity of A is 2I plus 3j, and the velocity of B is I minus 2j. It says in the question they're going to collide. Now, for simplicity's sake, with this one, I've said that the smaller particle is brought to rest. Find the speed of the other particle. Now, the layout of this, all right, the layout of how you set this out can make this very, very simple. And if you don't get your layout right on simple questions like this, if they start to give you harder questions, then you are going to find it difficult to do. So please think about how you're going to set your work out. Now, this is a question on momentum and impulse. Now, as I said, I'd like to look at the DAD system. So what we're going to do is we're going to have this one down here. This is going to be particle A of mass 2 kilograms. And this one up here is going to be particle B of mass 4 kilograms. Now initially this one is moving with a speed of I minus 2j, and I underscore my vectors. All right, and please make sure that you indicate that it is a vector term and not a numeric term or a letter term by not putting the letters in. The smaller particle is moving up this way with a speed of 2I plus 3j. This one I'm going to put this way. We're told that the smaller one stops, so we're going to have V1 equal 0. And this one we're going to do, I'm just going to put it down this way just for the indication's sake, V2. So technically it's V2 that we are looking to find. Now the work that you've done in FM3, the first thing that you'd have had in a linear momentum question, you'd have said, oh, I need to use the principle of conservation of linear momentum. This question is exactly the same. All right, this question is exactly the same. So we've got BP COLM by the principle of the conservation of linear momentum. So instead of writing that huge long sentence, we shorten it to BPCOLM. That tells the examiner what you're going to do. Now, according to the rules of the conservation of linear momentum, that tells me that the momentum prior to the collision is equal to the momentum post-collision, after the collision. So if I set it out in columns in terms of i's and j's, we've got the first one is twice m times v. So it's twice 2i plus 3j. And to that, we are going to add the second velocity, or not the second velocity, the second momentum, which is plus 4 lots of I minus 2j. And that equals the momentum after, which will be twice v1 plus 4v2. But the nice thing is that v1, we can immediately get rid of v1. That is 0. So that's quite nice, that's gone. If I remove the brackets on the left-hand side, that gives me 4i in the first column, plus 6i in the second column, 6j in the second column, I should say. And then underneath, plus 4i minus 8j. And that is equal to 4v2. So this implies that v2 is equal to 2i minus a half j. And there's the solution. As you can see, we've introduced vectors, but we're thinking about the columns. Anything in the I column can be added or subtracted together, but it cannot be added or subtracted to anything in the j column, and vice versa. So again, we're thinking about how do we set our work out so that it's easier to keep track of where things are. Now, obviously, moving on from there, what I've got here is the question from the specimen or the sample assessment material. Now, this was the material that was sent out in 2017 with the introduction of the new syllabus. And for each module of the A-level exams, be it mathematics or further mathematics, there was a specimen assessment paper. Now, this is the one from FM3 with regard to collisions in 2 dimensions, but as you can see, because of the way it's set up, it's I's and J's. Now, as far as this question is concerned, if we read the first sentence only, it says a particle of A of mass m kilograms has a position vector of 11I plus 6j. So effectively, that's my start place. It has a velocity of 2I plus 7j. Now, that means that if I want to know the position of where particle A is going to be in the future, it's going to be its original position vector, 11I plus 6j, plus where I end up, which is the distance. And from physics, the distance is speed times time. Now, obviously, we're looking here at velocity, not speed, but the concept is the same. So that the future position of A is going to be 11I plus 6j plus t times the velocity component. And the same thing will apply to B. Now, obviously it says that prove that the particles will collide, and then it tells you that the particles will coalesce after collision. Find the common velocity of the particles after collision. That's the big part of this question, is that we've got to show that they collide and then find the common velocity. The other two bits, they're saying, should come quite easy to you. Now, on the next slide, I've got the same question, but it's from the Welsh paper. So as you can see, when we look at it, the numbers are identical. Obviously, it's just written in Welsh. Now, in terms of the solution, what we have here is that for part A, at time t, we have that the position vector of A, which is R subscript A, is its original position vector, which is 11I plus 6j, plus speed times time, or in this particular question, velocity times time. So it's going to be 2I plus 7j, lots of t. Go back and finish that bracket. And similarly for B, the position vector of B is going to be 7I plus 10j, and then we're going to add on the velocity times time component again, which is 5I plus 4j, lots of t. Now, what we're saying is we want to show that particle A collides with particle B. Now, that actually means, if you think about this, this is going back to work that you've done at GCSE mathematics and in your A-level mathematics, in that there we looked at two graphs crossing each other. And the one thing you said there was, if this graph crosses this other graph, then we know that the x and y components are the same. So therefore, you always solve them by saying the y component of this equals the y component of that. And you ended up with an equation in x. We're going to apply the same principle here. Because they collide, right? So if they collide, this implies the position vector of A equals the position vector of B. And that's for some value of t. So what we're going to do is we're going to take the I component from the A vector, the position vector of A, and we're going to put it equal to the I component for the position vector of B. That will give us a solution for t. We then do the same thing for the j component. If the value of t for the j component is the same as the value of t for the I component, that means that my two particles will collide. If the values of t are not the same, then the simple option is they are not going to collide. The value of t must be the same for both I and j. So that's what we're looking at. So what we've got then is, for the I, and we're only looking at the I component to start with. So from the position vector of A, we have 11 plus 2t is equal to 7 plus 5t. And if we do the same thing for j, again, I'm indicating that it's a vector. I'm looking at the vector component. Hence, I've underlined the j, same as I've underlined the I. And so for the j component, that is 6 plus the 7t. And that equals 10 plus 4t. Now, if we solve the I component first, 11 take away 7 is 4. And 5t take away 2t gives me 3t. So this implies that t equals 4/3. The next one, 7 lots of t take away 4 lots of t gives me 3 lots of t. And 10 take away 6 gives me 4. So this implies that t equals 4/3. Now, as you can see, by working these out side by side, it's much easier to compare the value of t from the I component to the value of t for the j component, rather than do the I component and then carry on down the page and do the j component. So do them side by side. Now, when we make the comparison between the two values of t, we can immediately see that the value of t for I is 4/3. There's no units, so we don't know if it's 4/3 of a second, a minute, an hour. And similarly for j, t is 4/3. Again, is it seconds, minutes, hours? So, but the numerical values are the same. So as t is the same, so we have as t is the same, comma, the particles will collide. So we've proved what they've wanted us to prove. Prove that they do collide. Now, the next thing was to find the speed of the particle after the collision. And we are told that during the collision, the two particles coalesce. So that's effectively, if they're made from metal, as they collide, they melt and reform into a bigger sphere. None of the metal is lost, but it's just one sphere now instead of two spheres moving independently. So what we have there is, surprisingly enough, following on from FM3, we're going to BPCOLM by the principle of the conservation of linear momentum. Now that tells me momentum prior to the collision is equal to the momentum after the collision, post-collision. So what we have is we've got mass of A times its speed, which is 2I plus 7J. And that is added to the larger particle, which is 2m times 5I plus 4j. And that is equal to the momentum afterwards, which is going to be 3m times v. There is only one particle, so I can immediately just write it as a single letter. Now, the nice thing about this is that when they've described the situation, all the masses of the particles are multiples of the same basic unit. Now, the idea behind that is once you've written that line, from the work that you've been taught for your GCSE mathematics, you look at that and say, oh, there's a common factor there. I can divide everything by m. So that one goes, that one goes, and that one goes. So instantly, it becomes much, much easier for me to deal with. Now, if I expand the brackets, 2I plus 7j plus 10I plus 8j. And that equals 3v. Doesn't look like a 3. There you go. And please, can I ask that you ensure that if you're working in a question that involves the speed prior to a collision and the speed after the collision, if you're talking about u and v, please make sure that whoever is marking your papers can distinguish between the letter u and the letter v. U has a rounded curve at the base, v goes to a point. Please make sure it's that way, and then there's no opportunity for the examiner to misread what you've written. So that will give me that v equals 12I plus 15j all divided by 3. So therefore, v equals 4I plus 5j. And again, clear, easy. Don't try and do too much too quickly. As you move down one line, try to limit it to one, possibly two things that you're doing. As I've done from line 2 to line 3 on this particular slide, I've done two things. I've added up all the components on the left hand side, all the i's together, all the j's together, and I've divided by 3. So I've been a bit naughty, I've done the 2 things there, but again, it's easy to follow. Now, the next part wanted you to work out the change in momentum or the impulse. And remember that impulse is the change in momentum. So for part B, the impulse equals, so it'll be twice m 4i plus 5j minus twice m, because it's the same particle, 5i plus 4j. Now, as far as this is concerned, I'm going to take out 2m as my common factor, and that leaves me with 4i plus 5j minus 5i minus 4j. So the impulse is 2m minus I plus j. And that's Newton seconds. That's why that's only worth 2 marks. Pick one of them and you go with that. So this one, it was the impulse of A acting on B. So because it says on B, we do work out the impulse for particle B. So that's why it's done that way. Now, for part C of the question, what they're actually looking for is the loss in the kinetic energy. Now, this requires you to work out a half mv squared. Well, if you think about it, v squared in a vector sense is v dot v. Now, if you've got i's and j's, if you think back to the dot product, it means the magnitude of I times the magnitude of I times cosine of the angle between them. So for the unit vector I, the magnitude of I is 1. So it'll be 1 times cos 0. You should by now be well aware that cos 0 is worth 1. So we end up with the sum 1 times 1 times 1. So we can do I dot I and we end up with 1. Now, if we do I dot j, we end up with 1 times cos 90. And again, check on your calculator. Cos 90 is worth 0. So if I do I dot j, there is nothing. So I'm only allowed, when I do the dot product, I am only allowed to multiply the numbers in front of similar letters. So it's only the numbers in front of similar letters. Now, if we look at particle A, we've got a half mv squared, which is a half m 2i plus 7j brackets squared. So that's going to be a half m 4 plus 49, because I can do 2 times 2, the I bit times the I bit, to get 4, and I can do 7 times 7 to get 49. I'm not allowed to do 2 times 7, because I end up with I dot j, and that's worth 0. So I'd have 2 times 7 times 0. So it's gone. So that's the principle I'm working on. B then is a half 2m, and that's going to be 5i plus 4j squared. Now I'm going to write that as a half 2m. There is a method in my madness, and you will see exactly why in a moment. And that's going to be 25 plus 16. And then after the collision, when they coalesce, so it's A plus B, that's going to be a half times 3m, and that's going to be 4i plus 5j. Squared. And that's going to be half times 3m, 16 plus 25. Now, the loss in kinetic energy is going to be the kinetic energy of A plus B, the top two, minus the bottom one, once they've joined together. So what we'll end up with, so loss in kinetic energy equals 4 and 49 is 53. That gives me 53m over 2 plus 25 and 16 is 41, doubled it is 82m over 2. And then it's going to be minus, that's 41, so it's going to be 123 over 2. So that's why, I know we've got calculators, but that's why I didn't do a half times the 2 for particle B. So they're now all over the same fraction, and I've missed the m out on the end because I'm not focusing, I'm talking. You must concentrate. So effectively now it's 53 plus 82 minus 123 all divided by 2. And what we actually get then is we get 12m over 2, which is 6m joules. And be careful when you're putting the units in here. I tend to move it a bit further over just to make sure that the examiner doesn't confuse my units with the numerical part of the solution. So again, look at how I've set it out. And so much work that you're going on to do relies so much on work you've done previously. We cannot turn around and say, oh, well, we've done all that, I've been successful there, I'm moving on. You've got to bring everything else with you.